מה? לא, אף אחד לא מוקלט. בסדר, אפשר לבית, לא פעם.
יש, בואו נתחיל את הדקות ונמחק מלא.
לא, נראה לי אני לא יודע, אולי בסוף יבוא איזה שוטר. נראה לי אני צריך באנגלית כאן. נראה לי ש... זה לא משנה כל כך, כי כל המונחים הם באנגלית גם ככה. טעויות יש בשתי השפות. So we were just about to start go over together on the question page of the first. I mean, it's a bit confusing because we already started the second chapter about protein structure and function, and we reached about the middle of it. But now, conceptually, we go back and just go over again some concepts from this first chapter. So do you have it in front of you? Did you try it at home? So please do also for the next time. So the first question, so it's always the same. You can mark only one correct answer, not 2, 3, 3.4, only one, and then if there's more than one, you have to mark the one that's the full question. Okay, number 1. In what cellular functions is the adenosine base involved? So what do you think?
All of them.
All of them. So what about the stabilizing structures? That's the only one I would wonder about. Because I would immediately agree about information storage, as it is in the messenger RNA molecule, energy storage, ATP, and what about stabilizing structure? I'm not sure.
I don't remember when I typed it, but I think it's in the bonds between the that keep the protein folded in its special form. I think the adenosine base is involved.
So if anything, it will be in the structure of the DNA and RNA, because adenosine is a nucleotide. It's apart from nucleic acid and not from amino acids, which are the components of the proteins, right? So if the sense of what you're saying, only if you switch between protein and DNA or RNA, and indeed you're right in that there is a secondary structure that's stabilized by hydrogen bonds, and we'll see it actually, well, maybe the next hour of today or next week. But you know what? Maybe I'm not sure. Well, I can't really exclude this answer, but only because of the part explaining the double-stranded DNA, where it complements with another base on the other strand. So actually, yeah, I think I'll take your answer. All right. So number 2, following is a list of chemical building blocks and macrostructures. So we have both levels. Match each of the macrostructure with one or more of the building blocks from which it is built. So you're not told whether each one of these components is a macrostructure or a building block. You need to first identify which is which and then match between the two. So who wants to give it a try?
I thought the cell membrane consists of phospholipid.
Right.
The phospholipid bilayer.
Right.
The very first one. And I'm not sure, but maybe DNA and RNA can be macrostructures that consist of nucleic acid.
Absolutely right.
And polypeptide consists of amino acids.
Right.
Chain of amino acids.
Correct.
Yeah. And monosaccharides, I have no idea what to do with them.
Really? So monosaccharides. Yeah, what about the polysaccharide? Let's switch the mono with the poly. But okay, great.
Excellent. The nucleic acid, they are the DNA and the RNA, so they consist of them.
Well, I think it's a matter of terminology. So when the DNA molecule is actually usually used to say, well, you can say double-stranded or a single-stranded DNA. The DNA molecule is usually, I would say, 10 nucleotides linked together or more. And then each of these nucleotides is a nucleic. It's actually, chemically, it's a nucleic acid, but then actually the term is used also when describing the DNA as a whole. But to be more correct, nucleic acids are actually the component. I think it's terminology issue. Sorry. Number 3, what type of chemical bond exists between sodium and water? So if you place this charged ion inside aqueous solution, what would happen? You said yes.
I think it's a hydrophilic one.
Okay, so there's no terminology-wise again. There's no bond we call hydrophilic one. And there's a hydrophobic effect,
Okay.
right? Where two uncharged, unpolar substances stick together to lower the entropy. I mean, the background is the thermodynamic law of lowering of increasing, of course, of increasing the entropy. And okay, so if you place this out, there's actually a bond, an interaction, that you have ion in its name. So the ionic interaction, which is an electrostatic interaction between an ion and another ion. Okay, so in here, to be more precise, it will be hydrogen, or the negatively delta charged oxygen of the water molecule will interact with the positively charged sodium, this cation here. So, but we actually gave it as a specific example when we talked about ionic interaction. Okay, so ionic interaction. So we have it here, ionic bond. Okay. And the first
Just a
yeah?
question about number 3. Van der Waals bonds always exist, right? But it's like negligible here, or there's not so many in the site.
Yeah. Well, you have right. Well, the concept, the notion, usually the way people address it is, well, the random fluctuations are already there, and always when two atoms are close enough together, you could measure. There is a sense in talking about Van der Waals interaction, but when there's another force in the system, then by all means it governs.
Overcome.
Thank you. It overcomes and it just overcomes the other force. The Van der Waals bond. Remember, we saw it on a logarithmic energy measured by kilocalories scale. It's much weaker. Okay, the fourth question: monosaccharides differ from one another by what feature or features? So, in other words, when you look at different monosaccharides, what differences would you find between them?
A is definitely correct.
The number of carbons in the molecule, right? So we have different lengths for the chain. Yes.
And I think B is also correct.
Bond conformation around the carbons, definitely. So you can have a cis, a trans. You can have okay.
And the ring size because they still complete cycles.
Right. So the linear chain can bend and form a pentose, a hexagon, and so on and so forth. All right. And the polysaccharides they form. So different combinations of monosaccharides give rise to different polysaccharides. We have a few examples for the disaccharides mainly. So all of the above. Okay. So that was going back a week or two to basic biochemical of the cell. And now let's proceed with the protein structure and function structure. So we studied the hierarchical structure of proteins, where we saw that there are four levels of structural organization. We then described several modifications that proteins undergo after they are being synthesized, and the way they are properly folded. And I would put it an asterisk right here because I'd like to see a short clip about this second point with you in a minute before we start. And the third point was about a subgroup of proteins that promote chemical reactions. These were enzymes, and we will now proceed with molecular motors, another subgroup of proteins that are responsible for cellular motility, for movement in the cell. So in the website for the textbook, you have some nice movies. So let's watch the one that tries to show the sequence of events for the chaperone-mediated folding, which we described. So there are some details maybe that were not mentioned in class. These are less critical, but it's
In vitro, a denatured protein can refold into its native state on its own. Nonetheless, in vivo protein folding is aided by chaperones in order to increase efficiency and prevent aggregation of misfolded proteins. Molecular chaperones, such as HSP70, assume an open form when bound to ATP. In this form, the chaperones bind nascent polypeptide chains as they're synthesized on ribosomes.
nascent is as it is grown. Nascent means as it's developed, as it's being synthesized. Nascent chain is being grown.
The bound ATP is hydrolyzed to ADP. ADP exchange with a new ATP molecule causes the chaperones to switch to a closed conformation, releasing the target protein. A second class of chaperones, the chaperonins, is required to help a small proportion of proteins fold properly. A partially folded or misfolded protein is inserted into the cavity of the chaperonin, where it can fold into its native conformation. ATP binding causes the chaperonin to expand and release the protein properly folded.
Okay, in this context, we also mentioned class well, the notion that what happens inside is lowering the plane that in the plane of possible conformations for the folded protein inside the chaperonin. That the chaperonin decreases the plane and hence promoting the rate in which the folded protein will achieve its correct minimum energy, usually minimum energy native state. Okay. Let's continue with molecular motors. So again, in this group of proteins as well, what we will find is a conformational change or a series of conformational changes, as we saw in the enzymes. But in this time, these series of conformations couple ATP hydrolysis or chemical energy to become movements, to mechanical energy. Energetically wise, this is what these proteins do. Myosin is our main protein in cellular motility, and they all have, it's a small group of proteins, and they all have a distinct head domain, a neck domain, and tail domain. In their head domain, you would find two important sites. The first one is the actin binding site. Actin is another protein that serves as the scaffold on which movement will be achieved. So this is where the interaction with this protein takes place. And another important site in the head domain is the nucleotide binding site, usually in ATP. So this is right here. And then on the neck domain, you have usually, well, we will not go into the specific roles these two components play. You will find usually regulatory and essential light chains. These play a part in the conformational changes these proteins undergo. Okay, we will now, still on the wireless pointer, hopefully next week. We will now go over what is called the series of steps, or the cycle of actin-based motility. So this specific scheme it represents what happens in the muscles, where we will see that the thin, the thick filament is slided in parallel to the thick filament, to the thin filament, the actin filament. But the same thing actually occurs, the same steps hold true for what happens inside the cell. So for instance, you can imagine that instead of this thick filament here, this blue bar here, you'll have an organelle in the cell that needs to get from some place to another. For instance, a vesicle that's packed with neurotransmitters, that's packed somewhere around the soma, needs to get into the far to the synapse site. So the same molecular basis perform this task inside cell. But again, this one's for muscle. Okay. And the cycle of movement starts with the first step in which this is actually the baseline state when you have no ATP in the system, and hence the ATP binding site on the myosin head is free, unoccupied. In this state, the myosin head tightly binds to the actin filament, to its specific site on the actin filament. This is the red, I think, circle here. Okay, so this is where everything starts. So when you have no ATP in the system, the muscles actually are in a stiff state. And this is the reason why after death, when the ATP pool is washed out or it's done, so there's the phenomenon that's called rigor mortis, or stiffness of death. It's a bit maybe counterintuitive, so in less of soft muscles you find stiff muscles, and that's because, again, in the lack of ATP, the myosin head binds tightly to the actin site. Okay, so, and one myosin head is maybe not a big story, but a couple of millions in each muscle, then it's very hard to move the muscles in this state. Okay, and then you add an ATP to the system, and it binds into the ATP binding site on the myosin head, and this leads to a conformational change in the myosin head, and the myosin at the actin binding site, or the binding with actin, is disrupted, and the myosin head is released from the actin. Okay, so this is the second step, head dissociates from the cell. Next, there is an hydrolysis of the ATP to ADP, adenosine diphosphate, and alone phosphate. So the myosin head itself is the ATPase. It means that it can hydrolyze ATP molecules. In this stage, so look what happened. The myosin head switched the location forward to one direction on the actin filament, and again binds a new site on the actin filament. So up till now, there was no movement, right? So a movement will mean that this thick filament would slide parallel to compared to this filament, the actin filament. And up till now, none such movement has occurred. But now, when the lone phosphate dissociates from the ATP binding site, so this is what happens in the third step, that leads to what is called the power stroke. This time, the conformational change of the myosin head is such that the myosin head goes back to the initial conformation and cause a sliding of the thick filament to one direction. Okay, and it still has the ATP binding site. Dissociation of the ADP from this site brings us back to the first step. Okay, so these were the details.
So when you release the other, doesn't it convert it itself to AMP? The second bond is not released?
Not in this reaction. So the ADP is released from the ATP binding site as its adenosine diphosphate. Right. Okay. So that's the molecular basis for cellular motility. It's true for muscles. It's true for with minor differences in organelle translocation inside the cell, where the actin thick filaments are served as maybe highways or roads in the cell. Okay, so let's see another movie from the same website, again, just to see the sequence of events, like one after the other, then we'll proceed.
Myosin motility is coupled to ATP hydrolysis. The following mechanism pertains to myosin 2, but all myosins are thought to move the same way. ATP binding opens the cleft, disrupting the actin binding site. This causes myosin to release the actin filament. With ATP hydrolysis, a conformational change rotates the myosin neck and partially closes the cleft, restoring the actin binding site. Myosin rebinding to actin catalyzes phosphate release and activation of the power stroke. The final step of the cycle is ADP release. Movement of myosin along the actin filament continues as the cycle is repeated. In this case, the myosin molecule is tethered, so the resulting action is sliding of the actin filament.
Okay, so that was several motility. Any questions? Yep.
I can confirm you. The filament is much larger than the myosin.
The filament, which one?
Both of them.
Are much larger than what?
Than the single myosin.
The single myosin, well, I'm not sure about the ratio between these two components. And you have actin thin filament in several diameters you can find in the cell. I'm not sure. This is just a schematic, presentation.
No, what I mean is,
Yeah.
I wanted to ask, if the myosin works alone, if the ATP connects only to him and not to the other myosin, doesn't it damage the myosin, the conformational change, when it connects to the two filaments and makes the power stroke, if the two filaments can't move?
The ATP binds to, instead of the myosin, to the filaments?
No,
Sorry.
I'm
sorry.
not clear. If the ATP connects to the myosin,
Yeah.
and the myosin starts the power stroke or one of the conformation changes, doesn't it damage the myosin instead of how does it move the filaments and not damage the myosin?
Why doesn't the myosin kind of breaks down or rip instead of well, first of all, so in muscles there are several thousands of myosins that link these two filaments together, and if each one pushes just a bit, then you'll get a summation of a large enough force. And second one is proteins that have to do with cellular motility. I guess they are, strong enough in their structure as they are. I think. Is that kind of answer?
That was my question.
Okay. Okay. So second point is common mechanisms for regulating protein functions, and so we actually discussed several such mechanisms. So we will now just add a few more details or just make in order a bit. So first, as principally speaking, the catalytic activity of enzymes or the assembly of a macromolecular complex is regulated to meet the needs of the cell, and cells have several regulatory mechanisms to ensure that this is indeed the case. And that's an important term. So allosteric mechanism, it's a way of regulating proteins, but only a mechanism in which a change in a protein tertiary or quaternary structures induced by the binding of some other molecule that can be activator or inhibitor to any site other than the active site. Only these mechanisms will be called allosteric mechanisms. So again, let's start with the opposite of allosteric mechanism. If you have a ligand, if you have a molecule that binds to a protein in the active site of the protein and changes its function. So this indeed will be a regulating mechanism on this protein, but it will not be allosteric. And allosteric mechanism is any such change that will be induced by a binding of the molecule somewhere else than the active site. Okay, so proteins have other binding sites besides their active site. All right. Let's see several such examples. Okay, so one example of allosteric mechanism is cooperative binding. And in this mechanism, the binding of the first molecule to a protein changes its affinity, the protein's affinity, to the binding of the second molecule. So affinity is the tendency of a protein to bind the molecule. So this is the terminology. We talk about affinity between a protein and a ligand, how good, how tight is the recognition between two molecules would be. And if a protein, which happens a lot in the cell, if a protein has more than one binding site to its ligand, it can bind two or more ligands, as in this important protein here, calmodulin, which has 4 sites to bind calcium. So if the first binding of the first calcium would change the affinity of the second binding, and in this case will also change the affinity of the third and fourth bindings, then we would say that it is a cooperative binding. There is a positive and negative cooperative binding. If the first binding positive or increases the affinity to the second binding, we're looking at positive cooperativity. And if the first binding lowers the affinity of the second binding, that's a negative cooperativity. So for instance, again, for this protein, calmodulin, to be active, it needs to bind 4 calciums. And in this state, it changes conformally, and then it changes its conformation, and it can recognize specific target peptides. Never mind what happens next. But the binding on the first calcium would increase the binding of the second calcium, that would increase in its turn the binding of the third, and that will increase the binding of the first calcium. And so what we achieve is a higher gain for this protein. Subtle changes in the concentration of the ligand, in this case of the calcium, would have a robust enough effect on the activity of the protein, in this case of the calmodulin. It's like increasing the gain button in amplifier. Okay, so this was cooperative binding. Another example which we mentioned, I think, in previous class, is that ligand binding can induce release of catalytic subunits, or transition to a state with different activity. Okay, so release of some segments in the protein that turn the protein into an active state. So we mentioned it, and we will see a couple of examples later on. Lots of times we have molecules, regulating molecules, in this case GTP, guanosine 3-phosphate, for instance, that can push a protein from an inactive off state allosterically, by allosteric mechanism, to an active on state. The same thing we find with phosphorylation. So an inactive state of a protein that will be phosphorylated somewhere else than the active site will become active, and the opposite reaction will take it back towards an inactive state. Right, so we mentioned a couple of the components that are mentioned here. These are important components in allosteric mechanism: calcium, GTP, phosphorylation, and just a few common molecules in allosteric mechanism. Okay, so the next and last point would be a bit about the methods we have in the lab to purify, detect, and characterize proteins. And so first of all, obviously, in order to study a protein, its structure and its interaction with other proteins and everything you want to ask about the protein, you first need to purify it, or at least get an enrichment enough for the protein before it can be thoroughly studied. And you can separate or enrich or purify proteins based on any one of their many features. So, because each protein has its own pH, its own activity, its own ligands that it can bind, and so on. And the two most widely characteristics or features for a protein on which researchers usually separate them is size and binding affinity, or recognition to other molecules, to ligands. Okay, we usually start with a small piece of tissue, or we have a cell from some experiment. We start with either a cell or tissue, and then we homogenize it. Prepare a homogenate, which means that we just mechanically grain the tissue or the cell we harvest to get some mixture of floating proteins in the test tube. And we can then perform a very rough separation by size by centrifuging, spinning the tube very rapidly. There are lots of protocols and forces and times in which you can centrifuge different proteins and get different outcomes. But generally, you would, after enough time of centrifugation, a sediment is formed, sediment mishka, and a supernatant, tarchif. Here, there are the heavy ruins of cells, I don't know, fractions of cell membranes, maybe some dead cells that stay intact. And here there are the insoluble proteins, which we will take further to more subtle separation in the sediment and tarchif. שנייה שכחתי את המילה. Supernatant, sorry. Okay. So we take the supernatant, and we can now perform more subtle separation. For instance, by pouring the supernatant into a tube that includes a sucrose gradient. Right? So the matrix or the medium inside this tube becomes denser as you go towards the bottom of the tube. This is before the pouring inside the protein. This is what we bought from the store. And now you put inside the supernatant and you spin it around again. You centrifuge it. And because larger proteins will have a more significant force against the sucrose gradient, so they succeed in advancing more towards the bottom of the tube, where they will be found after a long enough centrifugation. And you can then separate, just take these sections of the tube and separate them into different test tubes. So in this protocol, these are the larger proteins that are found more towards the bottom of the tube. And the smaller ones, more upwards. But this is still a relatively rough separation, and we can then perform even further separation by a very common method. It's called Electroporation, which performs separation by size. And it starts with the treatment of SDS. It's a sodium desosyl sulfate. It's a substance that does two things. So first, it destroys any tertiary and secondary and quaternary structures that were there in the protein and leave us only with a linear chain of amino acids. So in electrophoresis, the only thing that plays a role is the primary structure of the protein. And the second thing we gain by the SDS treatment is that it increases the negative charge of these proteins. Okay, then these SDS treated proteins can be loaded in a gel that's usually a polyacrylamide gel. And the structure of this gel, if you zoom in, it's just a very dense mesh of the polyacrylamide, through which it's very hard for the protein to pass. Okay, then we induce an electrical field in this vertical axis, and the negatively charged protein migrates towards the negative pole, towards the positive pole, the cathode. Okay, now, because bigger proteins would have a harder time passing through the dense matrix of the polyacrylamide gel, after long enough induction of the electrical field here, there will be delayed, or there will be still somewhere in the middle in their initial point, compared to smaller proteins which will advance faster and hence will be found after, say, an hour, somewhere in the closer toward the cathode. So again, the smaller proteins will succeed to get closer to the cathode. Now, it's true that the larger proteins have more negative charge because they're larger and more SDS sticks to them, and then they're supposed to feel a higher electrical force. But the thing is that in this assay, because of the polyacrylamide structure, the main determinant, the main force that plays a part here is the fraction force that the proteins feel when they pass through the polyacrylamide matrix, and less so the electrical force that pushes them towards the cathode. So really the 99% of the feature that set by which the proteins are separated here are still their length or their mass, which here is the same because we've destroyed secondary and tertiary structures. Right? Yes.
So the drawing in the middle is not precise, right? Because it's supposed to be that all
The one in the middle?
all the proteins are starting like atoms.
From up, right? Yes.
Like a race.
It's like a race. So you have a whale at the upper part of the gel, and then you load protein. You can load, multiple samples of the same gel, and it's a race exactly, where the protein snakes their way through the polyacrylamide gel. The smaller proteins always win. They found more towards the cathode. Let's see this one right now. Okay, so this is what we've just described. Maybe we will get something.
Sds Polyacrylamide Gel Electrophoresis is a powerful tool which resolves proteins according to their molecular weights. Because proteins differ in size, shape, and charge, a protein sample is first denatured with the anionic detergent
Denatured meaning destruction of the secondary and tertiary and quaternary structure. The nature state of the protein.
SDS. When the sample is heated, the SDS molecules bind to the proteins and cause them to unfold. The denatured proteins become uniformly coated with negatively charged SDS molecules, so they all have a similar shape and charge-to-mass ratio. If a protein is composed of several subunits, the SDS not only unfolds the protein, but also dissociates the protein into its individual polypeptide chains. The mixture of denatured proteins is then transferred from the tube and loaded into a well that has been cast in the top of a polyacrylamide gel. In an electric field generated by a power supply, the negatively charged polypeptides migrate through the gel toward the positive electrode at the bottom of the gel. The migrating polypeptides are retarded by the tangled network of polyacrylamide. Smaller polypeptides travel more easily and quickly through the pores in the network than do larger polypeptides. Because the polypeptides have similar charge-to-mass ratios, the distance they travel through a gel is dependent only on molecular weight. Based on this principle, proteins are separated according to their sizes, with low molecular weight proteins having greater mobility than high molecular weight.
And then the endpoint again is this, where we get, biologists call this the lower band of small polypeptides and heavy bands that will be right here. When we read articles, later on in the course where they use this terminology. Okay, so this was separation by just one feature of the protein, their mass, and we can, yeah.
So it said it also differentiated a protein into its sub.
Yeah, absolutely. Yeah.
So how do you know what you're measuring is, how do you know how big the actual protein is of the one you're measuring? How do you know it's a combination of all those sub ones or if they're just different ones in different?
We a lot of times do not know. We don't know. So what we do, there's like a common pattern that you get in an SDS gel of certain proteins. So if you take a purified protein, you ask the Technion in Haifa to synthesize a pure protein that you want to investigate. For instance, a GTP protein. And then you get it and you run it in a gel and you know what bands you get. And then you extract something from a mouse and you purify it the best you can, and again you run it on a gel. Usually we get more bands that were in the artificial, and we don't know why. Or the bands would be a bit shifted upwards or downwards, maybe because they were glycosylated, or there were some modification that occurred in vivo, and so on. So there are many times where there are some modification, extra bands, stuff like that we don't know, or shifting of the bands, which we don't know how to explain. But this approach gives us two things. So one thing we'll see in the next slide, in which you can sort of quantify, what we call semi-quantify, the amount of the proteins that existed. And again, you can appreciate how pure your sample was. It's also true. So okay, so but again, a single protein that's usually built from more than one unit will be separated to several bands on an SDS gel. That's true. Okay, so this was, previous slide was separating proteins by just one feature, and here we can actually separate them by more than one in a two-dimensional gel electrophoresis. So the method starts by separation. The two elements in which the proteins are separated here are their mass and their isoelectric point. What is an isoelectric point of a protein? So if you place a protein in a pH gradient, somewhere between 4 and 10. Now proteins, when they move from one pH to another, they gain charge, they lose charge, up to the point where they become neutral. So if you add to this, or induce in the same vertical of the pH gradient, an electrical force, proteins will feel an electrical force and will start migrate if they will have some charge. Until when? Until the point where they have neutral charge, and then the electrical force is zero, and they will stop moving around. This point, the point that they will reach, is the isoelectric point, is the pH where they are neutral. So this was the description, and the accurate definition is, so the isoelectric point is the pH in which the protein is neutral. And empirically, this is how we measure it or find it. Okay, so proteins will be separated this way by the isoelectric point. These are the red bands. And now you just take this axis, rotate it in 90 degrees, and perform an SDS electrophoresis, as was described in the previous slide, that separates them solely by their mass. And then proteins having the same isoelectric point but different mass will be separated. Proteins that have the same mass but different isoelectric point again will be separated, and you open these two axes, and this would be the case if you separate only either by mass or by isoelectric points. And then what we get are these nice blots of proteins, where each dot here is a single protein. Okay, maybe a small group of proteins that have the same isoelectric point and the same mass. There's a study or an approach in protein research where you can perform this blot for one patient and this blot for a healthy individual. You can try to ask whether any of these spots decreases in size, in density, and so on, and thereby measuring their whole proteins or their pattern of the two-dimensional gel electrophore. Okay, let's take a 15 minutes break, and then we'll see.
be like, oh, now we're going to talk about this molecular mechanism. He knows about it. I thought that would be really interesting. So it's literally, yeah. But you, you what? The habit? Oh. Mhm. Yeah, yeah. Mhm. She presents with classes. Oh yeah, she's what is it called? Yeah. Intuitive. Yeah. Mhm. Yeah, I guess you have to take the class to be part of the course. The CNA. The CNA? Yeah. I'm only here for a year, so like I need to really know. It's really interesting. And the teachers are they're all professors. Yeah. So I guess we're meeting tomorrow at 11. I hope so. I mean, if she doesn't respond, then it's ask for him. You know? Yeah. I thought that's when it would be. I was surprised when she said, "Oh, let's take notes on it." I was like, and then she said like 7:30 in person, and I was like, oh my god. No, I thought she meant she can only have a class from 7:30 to 4:30 every day. Like after 4:30, maybe start losing focus. No, no. Oh, yeah, like you didn't know how long the class would be. So her ability. Do the experiments? No, but you go to her lab. I think she's teaching a lab class there. Oh, the research methods. Mhm. Pronunciation. Pronunciation. Sounds similar. Yeah. Yeah, because you're basically gluons. Yeah, that's awesome. Wait, is this green? Oh, we had it done. We had it extra high.
לפני 50 שנה עשיתי אלקטרופורז לקבוצות דם של אנשים כדי פרופסורים של אלקטרופורז.
אלישבע,
לא זוכר את השם שלו.
איך השם?
אלישבע גולדשמיט.
תל אביב, לא תל אביב.
מה? פה בירושלים.
אני אצל חרמון הסורק?
אני יודע, לא, אני בוולפסון.
אלישבע, טוב, אולי אלישבע אחרת אני לא.
יש שם נסיעה מודעת שם, היה לנו סעיף שעבדנו שם.
Okay, there's another a group of metals that enable us to separate proteins by different features, and globally they are called liquid chromatography, and the name comes from the German color industry in the 20th century, where these methods were developed. I did part of them. And the principle in all of them is that molecules are passed through a column with a specific matrix, a specific medium in it. Usually these are beads with different characteristics, and the proteins that interact, the molecules that interact with the matrix inside the column are delayed because of this interaction, and thereby exit less from the column. So this is the principle in all liquid chromatography methods. Again, that the interaction of the molecules with the inside of the column delays their passing through the column. You can then collect them separately. So the first example of liquid chromatography we'll mention is the gel filtration chromatography, which separates proteins by their size. In this method, inside the column, you'll find tiny beads with very small groups scattered around the surface. And when you start with a mixture of large and small proteins, the smaller proteins interact or are delayed while they're inserted, and again interact with the small grooves on the beads, and hence the passing through the column is delayed. The larger one, it's a bit maybe counterintuitive, but this time the larger proteins exit first, because the smaller ones interact with the beads, thereby exit last. And you can, again, elute the proteins and separately and put them in separate test tubes.
Can you explain why the smaller ones interact more with the beads than the bigger ones?
Simply because the characteristics of the beads, the smaller ones interact with the beads because of the size of these grooves, these crevices around the beads. If the crevices were bigger, then the larger one would interact with them as well, so the separation wouldn't work. So again, it's a bit maybe counterintuitive in gel filtration, because larger proteins have more trouble passing through anything, and hence will exit less. Well, not here. Again, you always need to think what is the metric, what's the characteristics of the matrix of the column, and anything that interacts with it is delayed, and hence exit last. Okay, that's the principle. Another example of chromatography is ion exchange chromatography. Okay, this time inside the column you'll find beads that are negatively or positively. They are positively charged. And if you pour in the column a mixture of a negatively and positively charged proteins, so this time because the beads are positively charged, the negatively charged proteins will interact with them. Right, the blue negatively charged proteins will interact with the positively charged beads, and their advance through the column will be delayed. And actually, in this case, they will really be stuck in the column. So first, we agreed that we achieved separation. Positive and neutral proteins have passed through the column, and the negatively charged are stuck inside. But we still want them in a test tube down there. So we can now add increasing concentrations of salts that we break down to an ion and a cation, and in high enough concentration, the anion, the negatively charged component of the salt, would exchange the interaction of the negatively charged proteins, and they would be pushed out or eluted. with the terminology. It will be eluted out. So again, it's about the interactions between the beads and the right proteins. Okay, this is the way we push them out. Okay, another last kind of liquid chromatography is affinity chromatography. And in this instance, in this example, okay, so now the beads are covered by a molecule, with a molecule that recognizes specific kind of protein. Molecules that interact or recognized by or recognizes proteins are called antibodies, and they are they are linked to the beads. And then any protein that will be recognized by this antibody would be delayed in the column and will then be delayed and then exit last. And to be more precise, so proteins with higher affinity to the antibody will exit last than proteins with low affinity to the antibody. Okay, so all these procedures include, specific protocols for washing and so on, but these are the principles. Okay. So there are specific, so we talked about purifying proteins, and now a bit about detecting them, or quantify them as much as we can. So there are specific enzyme and antibody assays that can detect individual proteins. Okay, sometimes enzyme assays are based on either measuring the loss of the product, or the loss of the reactant, or the gain of the product. When what you measure is the amount of an enzyme. So if we are looking for the amount of an enzyme which promotes this chemical reaction, these are the reactants, and these are the products. We can either measure how fast the products are formed or how fast the reactants are break down. And again, so the higher the enzyme concentration, the faster this reaction will take place. So we can measure either the left or the right side of the chemical equation. Some enzyme assays, a lot of them, utilize chromogenic substances which either gain light or change the absorption of the light. You can also, okay, so usually it has to do something with measuring, the reader is usually the absorption or the emission of the light. And if these, in the case where the substrates that you try to measure are not naturally chromogenic, there sometimes are, but if they're not, then you have a lot of companies synthesizing for you, artificially linking what you're looking for with the chromogenic substance, so you could follow the molecule you're looking for. Okay, so you can either look for a naturally chromogenic molecule, or you can just artificially link it with a chromogenic substance. Okay, another method to detect, specific method to detect protein, which takes the endpoint of the Sds electrophoresis further on. It's maybe the most common way to detect a protein in biology labs. It's called Western blotting. Western, after the investigator who invented it. Okay, so this is the endpoint of the electrophoresis, where you have separation by size, the protein length, and then this is a gel, polyacrylamide gel. You then induce an electrical force, this time perpendicular to the plane of the gel, and you transfer these proteins into a nitrocellulose membrane, on which you would be able to do further procedures like staining with different antibodies and so on. But so this is why it's called a blot, because whatever was here is now transferred to the membrane. Okay, and then you have several bands, which are several different proteins or several subunits of a single protein, and you want to mark just one of them. So, okay, usually staining with an antibody include two steps, or two antibodies: a primary antibody that recognizes the protein under investigation, and a secondary antibody with an enzyme in its end, and this secondary antibody recognizes the primary antibody, the first antibody that was used. So this enzymatic tail right here, or it is an enzyme-linked antibody, it's called. When you pour the substrate of this enzyme on the surface of the cytocellulose everywhere, so only where you will have the enzyme, and it's stuck right here because it's stuck to the primary, which is stuck to the protein under investigation, which is right here because of the electrophoresis. Only then you will get fluorescence because the enzyme turn the substrate its substrate to a fluorescent substrate. You gain fluorescence only where you had the enzyme, which is right here, and the substrate that you poured all through the plane. So let's see a movie to show the sequence of events of this event.
Can you explain again why did you do the electric current in this?
So this is just to push these proteins outside of the gel and into the nitrocellulose.
Immunoblotting combines the superior resolving power of Sds Polyacrylamide Gel Electrophoresis with a highly sensitive antibody binding assay to detect the specific protein in a mixture of different proteins. Proteins are first separated in an Sds polyacrylamide gel. Then, in the blotting step, the proteins are transferred to a sheet of nitrocellulose membrane. The gel containing the separated proteins is placed on the membrane. Protein transfer is done by electrophoresis. In the electric field generated by a power supply, the proteins coated with negatively charged SDS migrate toward the positive electrode. As the proteins migrate out of the gel, they are captured on the membrane because nitrocellulose binds any protein that contacts it. The proteins stick to the membrane in the same positions they had in the gel. Thus, the membrane is a blot of the gel. The gel is discarded, and an inert protein such as serum albumin is then used to coat the membrane so no other proteins will stick. A primary antibody, chosen to specifically bind only the protein of interest, the red one here, is then added. The albumin coating keeps antibody from sticking directly to the membrane. After a washing step, only the primary antibody that is bound to the red protein remains. Several methods are used to detect the antibody-labeled protein. All use a secondary antibody which binds specifically to the Fc domain of the primary antibody. In one approach, the secondary antibody is linked to an enzyme, so its location can be determined by a chromogenic reaction. The enzyme cleaves a substrate to produce a colored product that precipitates onto the membrane near the antibody. The blue-colored spot on the membrane shows the location of the enzyme-linked antibody and thus the position of the protein of interest.
Okay, so the use of primary and secondary antibodies are for two purposes. First, you get amplification. So you see, for instance, just for one target protein, you get, I don't know, 3 primary antibodies, which then amplifies to more than 3 secondary antibodies. And second is it's a versatile. It allows you for a lot of versatility in the lab. So if you have a primary structure for protein X and Y, you can use a primary antibody for protein X and separately a primary antibody for protein Y. And then you can sometimes use the same secondary antibody for both primary antibodies because they recognize both, but you know which one you use, and then you know which protein you look for and which protein you found. So again, it just allows us to play with different combinations of primary and secondary antibodies. Okay, so this was Western blotting, and the two last methods that we'll mention are for characterizing the structure of a protein. We'll go through them very briefly. Just mention them. So X-ray crystallography, that's a method to decipher the structure of a protein, it starts by the limiting step, the hard step in this method is achieving the protein crystal. So a protein crystal is several hundreds or hundred thousand, up to millions of units of the molecule aligned in the same relation or the same orientation in relation to one another. So they have to be, and this is why they're called a crystal, and it's quite hard to form such a crystal. It takes a lot of trials, a lot of failures to find the optimal parameters to achieve this crystal for each protein separately. Then, through this crystal, an X-ray is passed, and you read the scatter that's from the other side. Now, the mathematics takes this distribution of the X-ray that was formed by the crystal and turn it into coordinates of atoms in space. It exists for several decades already, but we still don't have the structure of each and every protein in nature, and it's not because we don't know how to interpret this pattern right here, but it's because we have not yet achieved crystals for each and every protein. This is, for instance, the reason for the Ada Yonat Nobel Prize, because she crystallized the ribosome, which is a huge machinery of proteins and other molecules that synthesize other proteins, while other researchers have failed to crystallize much smaller proteins. So she did it for the ribosome, something like a mouse and a car, maybe. She's the ribosome and other proteins, size-wise. So, okay, and with the first article we will read presents a model that's based on crystallography. And the last one we'll mention is another method for getting the coordinates of atoms in space for a protein, but that only works for relatively small proteins, somewhere below 20 kilodaltons in mass, are nuclear magnetic resonance, NMR. Okay, in this method, a solution of proteins is inserted inside a magnet, and then different radio frequencies are projected onto the solution, and the energy that is discharged from the protein, very briefly, is the pattern of the energy that's discharged can be transformed into coordinates of atoms in space. And obviously, the advantage here is that you don't have to form the crystal, which is a very hard thing to do. But it's only true for small proteins. Okay. So this was crystallography and NMR. And that's about the protein structure and function, a big protein. So first of all, go over again all the material. If you have any questions, of course, don't hesitate to ask me, or any questions that anyone would ask me by email. With your permission, I would send to everyone anonymously. I wouldn't say who asked it if you want. I don't know if you might or not. And then I'll give the answer. And so you are very welcome to send questions. And for next time, so you are requested to read the article Subunit Arrangement and Function in the NADA receptor. I sent it by email last week. I'll send it again after class. Okay, so now while reading it, try to, or ask yourself, what is the purpose of the article? What were the methods that were used to answer the main question and the sub-questions that are represented in the introduction and along the article? I guess there are some terms that we have not mentioned in class, so I don't know, read it with the open Wikipedia window. Anything that's not clear, just give it a glance. And then next week we will go over it together, and I'm sure that everything that was not 100% clear, I hope that everything will be 100% clear after that. Okay, that's that. And now we will proceed to the next chapter. And now the next one is really to put us all on a common ground concerning very basic terms in biology, transcription and translation. The transition from DNA RNA to protein from DNA to RNA, from RNA to protein. Anyone with a background in biology, I expect it to be a bit too trivial for you, so I would not be insulted. You are really welcome to leave if you want, and I can show you again what are we going to talk about. But anyone with no biological background, this is really essential. So first of all, it's forwarded to the first chapter in the textbook. We will mention transcription and translation, just a bit about the components that perform these processes, and a bit more about the structure of DNA, RNA. Right. So again, the biologists are familiar. Okay, so first of all, this is actually an overview slide. We will go over each of these steps in the gene expression pathway that's presented here, which is also called the central dogma of biology. Already here, I'd like to emphasize the different roles fulfilled by nucleic acids. So they store information in the form of DNA and messenger RNA. They are the sequence interpreters in the form of transfer RNA, tRNA. They're also part of the ribosome, ribosomal RNA, rRNA. Okay, we'll see this more soon. Let's put these things in spatial context. So DNA is localized to the nucleus, a membrane-bounded organelle in the cell, and it is there being transcribed through a transcription process, transcribed to RNA. The RNA undergoes several modifications, which will go much deeper in future class, and then leaves the nucleus to the cytosol, where it meets the ribosome, the gray spheres here, and it is being translated to proteins by translation. A reminder of how nucleic acids look like. So you have the sugar base, the sugars here, and the phosphates and the bases. This is the alternating part of nucleic acid. The phosphodiester bond between each nucleotide. We have the phospho and a link to an oxygen, which we call phosphodiester. What are we looking at? Is this DNA or RNA? DNA, because here in RNA, instead of a hydrogen, we have hydroxy. And this is why DNA is called deoxyribonucleic acid. Sorry. Okay, it has two defined edges, the chain of nucleic acids. One edge, which the carbon that's marked 5, the fifth carbon in this structure. There are rules of how to count carbons in a ring structure. Never mind the rules, but one is numbered 5, so it is the 5' end of the RNA, or of the DNA, sorry. And the other side, where the third carbon is exposed to the downward, is the 3' end. So this was the reminder. We talked about most of the things in which. Okay, the DNA structure is a double helix, meaning that it is composed of two strands, two separated molecules of DNA. If I would unwind them, so this is what I'll get. You have the blue and the red DNA strands. And then they are roped around each other to form the DNA, the double helix. Okay, in the double helix, the sugars and the phosphates project outwards. This is the red and the blue spheres here. And the bases, which are the alternating part in nucleotides, face internally into the internal part of the double helix. The interactions between the bases are hydrogen bonds. They are also called Watson-Crick interactions, after the researchers who deciphered the structure of the DNA double helix. So these are the interactions that stabilize the link between the two strands. In the DNA structure, after the two strands are roped, so we have a major groove and a minor groove. region and this region, and these are the regions through which, upon which proteins that recognize the DNA act upon. This is where they recognize DNA. Okay, we mentioned the orientation of the two strands is anti-parallel, so we define the 3 and 5 prime end. So while one strand goes from 5 to 3 prime end, the other one goes the other way around. And the Watson-Crick interactions, which we mentioned, is the consequence of, or the complementarity is a consequence of size, shape, and chemical composition of the bases. And again, I'm just reminding you that furines interact with pyrimidines. These are two different kinds of bases. All right. Besides, one more thing to mention. Besides the Watson-Crick or hydrogen bonds between the bases, so because you have a lot of atoms dense in relatively small size, you have a lot of Watson-Crick, a lot of van der Waals interactions going on, and also in some parts of the DNA double helix hydrophobic effect. This is the classic canonical structure of the DNA which you will find in any cell, and you'll call it the BDNA structure. You can characterize it just a bit. So it has, you can measure its diameter. It performs a complete turn every every 10.5 pairs of base pairs, which are 3.6 nanometers in length. So this is the BDNA, again the canonical one. And other structures have been observed for DNA, the more compact, again right-handed form of DNA, which is called aDNA. So the canonical, perhaps I haven't mentioned, but it's a right-handed double helix. And the A is again a right-handed double helix, only more compact, more dense in the vertical axis. And the zDNA, which is a left-handed double helix. And these two last structures are observed for quite a lot of time now in vitro, in laboratories, and evidence are being accumulated. People report that they see them also in cells, so they are thought to have a functional biological roles. For instance, something in transcription that we will see in a minute, in what is called the transcription bubble. So I will show it in a minute, but just mark these two structures, and I'll show you their function in the transcription bubble. All right. So these are the three known DNA structures. Okay, a very important thing to note is that we also mentioned a helix in proteins when we talked about proteins, but there, okay, so we have this is protein. So we have a helix in proteins and we have a helix in DNA. But note that while the hydrogen bonds that stabilize the alpha helix in proteins were parallel to the axis of the helix, because there were hydrogen bonds between the chemical groups of the backbone, blah blah. You can check it out later. But these were the orientation of the hydrogen bonds in the protein helix. In the DNA helix, the bonds, again hydrogen bonds, are in this orientation. They are perpendicular to the axis of the helix. Axis of the helix, which I'm talking about, is this axis. And so it makes it very hard to bend the protein when you push it perpendicularly, but you can do it very easily for DNA, because there's no force to oppose it, and indeed it plays a part in DNA recognition. For instance, when a protein is called TATA-FOX binding protein, TATA is a sequence from the DNA, TATA, which is the base is TATA, and the protein recognizes this short sequence, and when it does so, it bends the DNA very sharply like this. So binding of DNA is the DNA is a very flexible molecule compared to the protein. And indeed, it's been very tightly packed in the nucleus, and it can then be opened again and so on. This is part of the reason why it's possible. Okay, let's describe briefly the steps in the process of transcription, turning a DNA to RNA. So the first step is that the protein called RNA polymerase scans the DNA, encounters the start site on the template strand on the DNA. There's sequences that serve as a start site to it. Okay, and then the transcription bubble is formed. The two strands of the double helix annealed or unwind, and because you have to make one of the sequences exposed in order to synthesize an RNA according to it. Okay, and this is the transcription bubble. And if you take two rubbers wrapped around each other and will start open a transcription window or bubble, you will accumulate tensions in these two edges, right? You can just try. And it is thought that the Z and A forms of the DNA absorb some of these tensions right here. So I'm not sure if people have already observed these structures right here in this spot of the transcribed DNA, but this is what people will talk about right now, for these two endoteric structures of DNA. Right. And then the third step is the synthesis or promotion of the phosphodiester bonds between the RNA, between the bases is started to be formed according to the DNA strand, and this is the initial step of the synthesis, and terminology-wise, it's the last step of the initiation. And then elongation is where lots of nucleic acids are being added to form the nascent RNA. Again, nascent RNA is being formed using the template of the DNA. So you have a region here in this step of a DNA-RNA hybrid region. So DNA and RNA maybe less, when they hybrid, they can hybrid each other, maybe a bit less stably, but indeed you find this hybrid sometimes. Okay, and then when the polymerase meets a stop codon, a certain sequence on the DNA, it dissociates from the DNA and also the completed RNA molecule is formed. Okay, this was a very shallow description of the transcription machinery, but sufficient for our proposal. Okay, most cellular RNAs are single-stranded. Inside cell you find RNA molecules usually single-stranded, and they can form secondary structures, well-defined secondary structures which have specific functions. Here are some examples: hairpins, stem and loop, and pseudonodes. These are just three examples of such RNA structures. So in RNA, as was the case for proteins, it makes sense to talk about the primary structure, which is sequence of nucleic acids, and the secondary structure, which is the outcome of local complementarity between the bases in RNA. Some RNA molecules also make sense to talk about tertiary structures, but usually we stop in secondary structures.
Yes, are the complementary bases random, actually, depending on the code of the DNA?
Right. So it's well, you said two things. So again, the first thing is absolutely correct. So it's according to the sequence that's here in the RNA, which is a picture of what was in the DNA. And now it's not, well, random or not. It's again, if you have here a line of 8 to 10 bases that will interact with the bases right here. So yes, so complementarity will be achieved, and the secondary structure will be stabilized. And so what do you mean by random?
I mean that it's not like in the DNA where all of the sequences complementary to the
opposite strand. Right. So here, lots of times you have this local folding on the molecule folds on itself, on certain regions on itself, and yeah. So that's true. And yeah. And again, so there's a family of molecules that are called. There are small regulatory molecules called microRNAs. We will meet them when we get closer to the end of the course. But they have these structures in all of them. So it's in this sense, I was yes. In this sense, it's not random. It's a feature that RNA molecules have. Okay, we are looking at the gray spheres again as a ribosome, and this is just to give you a short description of how transcription occurs. Oh, sorry, of how translation occurs. So we have the messenger RNA molecule, the red one. We have the ribosome, which catalyzes the reaction I'm about to tell you about. And then you have each time a tRNA, a transfer RNA, which are molecules that recognize, because these are RNA molecules, so they have a specific 3 letters right here. The genetic code is a triple code, a code of 3 letters, 3 bases that turn into an amino acid. So they present in one side of them 3 bases that align with certain codons on the messenger RNA, and in the other side they just link, they hold an amino acid. And then when you have a certain codon, you will have an certain amino acid, specific amino acid inserted into the right site in the ribosome, which will catalyze the link between these 2 amino acids, which is which link? In polypeptide, it's called the peptide bond, because it's a bond that's in peptide. And then you gradually get a nascent chain of amino acids. Okay? Again, just note the different RNAs, because this is the confusing part, I know, for some of us. So again, messenger RNA maybe not process, store information, transport information, something like that. tRNA are the transfer RNA, they are the sequence interpreters. Why are they the interpreters? Because in one side they speak one language, and in the other they speak the amino acid language. And ribosomal RNA, you don't really see them. They are in the gray sphere, part of the ribosomes. Okay? So, about the genetic code. So as we said, it's a triple code, and the common way to represent the triple code or the genetic code that is a transformation from the domain of nucleic acids to the domain of amino acids is by this table, which shows the first, second, and third position of the third bases in the triple code. So, for instance, U will mean phenylalanine. G would mean leucine, the amino acid leucine. So this is the way you read this table. Okay, and a few things to note about the genetic code. First of all, it degenerates. It's degenerated to some extent, because you have 64 possible combinations of triplets, because you have 4 times 4 times 4, and only 20 amino acids that that exist. And that is because some codons, some triplets codes for the same amino acid. For instance, UUC, these 2 and these 2 code for the same amino acid, in this case serine. Okay, and this is biologists call these different codons synonyms, because they are like synonyms in a language where you have 2 different words that have the same meaning. So the words are the codons, and the meanings are the amino acids. And the second thing to note is that some codons do not code for an amino acid, but for a stop codon. So this is where translation stops, when you have UGA, for instance, or UAA, or this one. And regarding the start side of translation, so it's always started in methionine. So AUG, which codes for methionine, that's the start side of translation. Okay, so So that was the genetic code. And we'll end by going again quite briefly about the different steps of translation, which we've already kind of mentioned most of them. Okay, so the ribosome holds the messenger RNA, and then it lets tRNAs to be inserted into what is called the A site. This is where a new tRNA is inserted. Again, the first amino acid will always be methionine because of the codon, because of the start codon. Then it promotes the peptide bonds between these two amino acids, 1 and 2. This was this reaction, peptide bond formation. The tRNA, let's move to this. Sorry. The tRNA that stood in P and A sites of the ribosome shift leftwards to the E and P sites. E is for exit, is where the tRNA will exit, and a new tRNA would be inserted here, and a new peptide bond would be linked with between the second and third amino acid. This whole reaction is exactly what the ribosome promotes. And in the background of this process, outside of this slide, but a very important thing that happens is that you have tRNAs are loaded with the correct amino acid. Because obviously, incorrect amino acid on incorrect tRNAs would form mutated proteins, would form defective proteins. Right. So if the interpreter doesn't know the language, so that's a problem. Okay. So this was a very brief chapter, again, just with the hope to put us all in a sort of a common ground regarding these concepts. Anyone who this is the first time hears these concepts, please go over them again and read about them just a bit more. That's it. So I'll meet you next time, and we will start with the articles. Okay. כן, בדיוק. פה יש קומפלמנטריות, נכון? כן.
ובעצם מה שהתחלתי מהאחריות, זה נראה שבמקרה יהיה לך פה סרטיפמנטים שהם יתחברו.
אז תראה, ה-RNA, המולקולות האלו הן מגיעות מה-DNA. Any sequence that's there in the DNA will be transcribed to RNA, and then you get, so for instance, sequences, they are palindromes. They can be read from two sides, they have the same meaning, and sometimes palindromes link themselves.
Or differences of it?
No, not on the one. Yeah, palindrome sequences will form these kind of secondary structures.
So it's not really random because
it comes from the DNA.
Because it's a palindrome is it supposed to bind on two sides.
So it's supposed to bind
on the two sides and then form this type of
כן, כאילו אני פשוט הרנדום שאנחנו משתמשים
כי לא הבנתי למה כאילו איך אתה יודע איך בכל DNA יכול להיות שנוצר דפוס כזה אבל הוא אומר
actually usually an RNA molecule is a single strand that's linear open like the messenger RNA right here. In some RNA gains secondary structures thanks to local complementarity. Yeah, makes sense?
I don't think I have your email or got the link.
You need, so my last email which I sent, I think you wrote me an email and it didn't reach. You didn't get it?
No.
Sorry. Maybe I misspelled it?
Yeah, what is it?
So mine is, let me write it, that one? Just anywhere?
Yeah, anywhere is fine.
Maybe you should write it up.
Oh,
What?
that looks familiar. Maybe I
Most likely my photo.
Okay,
זה
I'll put
אותו
it
דבר,
out.
אני סתם שמות של דבר.
היה מאמר גם?
לא קראנו, רק הקרוב.
בסוף יש מבחן?
אז יש, אבל
לא צריך אותך מוצא נכון?
של המבחן? לא, אז אמרתי, אולי אני אכתוב את זה בזה. זה בשיעור האחרון של הקורס. זה יוצא שנייה לפני.
ב-17 כאילו?
זה נראה לי 17? טוב, אני חושב...
זה בדיוק בזמן של... אוקיי. יש נראה לי נכון, ל-11 עד ה-14, את של עידן סגל פה באוויר, לראות שזה בדיוק אז.
איזה כאלה?
פרונטיז...
הפרונטיז נושא פה, אני אבדוק את זה, זה פורום מרכז?
לא, אני לא יודע אם זה פורום מרכז, אבל אני חושב
אז זה 70% מבחן, זה מבחן אמריקאי, זה 30% עבודה, שזה מאוד קצר, העבודה היא עמוד אחד, אתה קורא, אתה בוחר מאמר, אחרי זה ניתן את הפרטים של
זה כאילו אחרי
אחרי המבחן נעשה זה, כן. כאילו העבודה כבר תוגש בסוף בתקופת מבחן, אז ניתן אותה חודש לפני סוף חודש, שאתם אומרת, זה לעשות אותה, ואז בוחרים מאמר, ואז כאילו עמוד אחד, יש איזה 3 שאלות שעונים על המאמר, וזה 30%. אז המבחן הוא תמיד בשיעור האחרון של זה, כי אחרת פשוט זה נכנס, כאילו, אף אחד לא מוצא. קיצור, אחרת זה פשוט יותר סיפור אצלי, אבל אני אבטא את העניין בקורס, עם הכמש. איך השמות? אני עושה בשמות
מנחם,
מנחם. כלם? מנחם כלם. סבבה.
עידן. באת קודם על התנועה של השריר, מה קורה שזה זז מהצד השני הפוך? כאילו יש יוצא כאילו ניתוק ואז...
כן, הם ממש נפרדים. ה-ATP נשטף, גם יש לך מלא, כאילו מה זה נשטף? ה-ATP עובר הידרוליזה נורא מהר. מיומין הד הוא ATP על מסתר. תקרב אליו ATP, כאילו התנועה הזאת של זה, כן, זה כאילו קורה וזה, ומיד מפרק את ה-ATP ואז גם...
מה קורה בצד השני, כאילו מהצד השני של אותה רקמה?
לא.
רקמה שזה פעם אחת צד אחד ואז פעם אחת צד אחד.
השחרור, שנייה, דבר ראשון, תראה, כל מה שאני יודע לעשות זה להתכווץ, הרי אין כוח שמותח שריר.
נכון, אבל זאת כאילו משוחרר כדי שהשריר השני יוכל
אבל נכון, אז בסדר, אם אתה מכווץ את שתיהם כלום לא קורה. אז דבר ראשון זה באמת שרירים אנטגוניסטיים, זאת אומרת שזה מתכווץ והוא רפואי, אבל גם מחוברים הרי. בחוט השדרה, שניהם הולכים לאותו נוירונים בחוט השדרה, והם עושים איניביציה אחד על השני. כאילו רוב הזמן לעשות, אתה לא חושב על זה בגלל שאתה מוסיף את השריר הזה, זה מיד עובר איניביציה. מוחית, אבל לא מכני. ואם אתה לא חושב על כלום, אז זה היה מתפתח עד שאתה מכני.
נכון, זה לא, אחרת זה משהו של שחקנים שמותחים את שני השם ביחד.
כנראה. זה כאילו מתיחת שריר?
זה משחק מתיחת שריר, זה
תפוס
משני הצדדים.
כן. אז זהו, אז השרירים האנטגוניסטיים מחוברים בחוט השדרה אינהיביטורית. זה לא נמצא בפיזיולוגיה וזה. זה אתה יכול לראות, אתה פותח עכבר, אתה מגלה בצד אחד, אתה יכול לרשום, הספייקים בצד השני פשוט עוברים אינהיביציה. זה מאוד ברור, כאילו זה... יש משהו שהוא נכון בביולוגיה סתם.
תודה.
שחר, מה שאמרת, עם המבחן והעבודה הזה על הקורס הזה?
על הקורס הזה.
אמרת את זה בשיעור הראשון?
כן, אז זה 70%. אז שמעת את הפרטים?
70% ו-30% שזה מה?
זה עבודה שבוחרים מאמר, וכאילו עושים דבר דומה למה שנעשה אצלנו.
מה שנעשה על המאמר הזה,
כאילו כותבים, עונים על 3 שאלות בנפח עמוד אחד, 600 מילה
והמאמרים זה מתוך רשימה או כל מאמר?
לא, אתה בוחר מאמר, אבל אני כאילו... אני מאשר אותה, זה כן, שזה לא יהיה משהו שהוא לא מתאים.
והשאלות זה כאילו שאלות מובנות כאלה?
שאלות אמריקאיות לגמרי, כמו השאלות שאנחנו עולים בסוף כל זה פרק, אז ממש זה לקוח מאותו הבנק, וגם אותו דרגת קושי.
לא, השאלות על המאמר, כאילו.
לא, השאלות במאמר זה משהו אחר, זה אני אביא לכם לקראת סוף.
אבל זה כאילו שאלות שאתה נותן?
כן, ניתן 3 שאלות... כן, מספור, זה אפילו ממוקדות. איך השם שלי?
גל.
גל?
כן.
ויטמין 8 לא דווקא מצליח גם יפה. כן. זה הרבה בשביל משהו שהוא רק
ויזואלי.
רק ויזואלי, כן. אבל לא אכפת לי, אז לא עושים.
כן, לא חושב.
זה עם חטא ואמץ. זה בסדר. אני מבואס, כי נורא רציתי להצליח.
תקשיב, מההתחלה דיברו על זה. הוא כאילו שואל אותי, הוא בדיוק מה שאני טוב בו,
כן.
אנשים שעושים את זה, כאילו כולם כזה מורפים, כאילו הייתי עושה את עצמי ברגע, יש משהו חוץ מ-ICMC?
אני לא יודע מה ההבדל כל כך, חוץ מתנאי קבלה.
תנאי קבלה הרבה יותר קלים, בגלל טיפולת יותר קטנה, ואנחנו יכולים, כאילו, כל השאר זה אותו דבר, חוץ משאר זה שאנחנו יכולים לדחות את התוכנית לימודים. כאילו, באופן הרבה יותר גמיש. כאילו, גם במוח התנהגות אפשר ישיר לדוקטורט מוצאים, גם זה, גם אותם קורסים, סלקטיבי זה כאילו, שלא מחייבים את העניין שכאילו הרבה קורסי השלמה בשביל לא הגיע מהנדסת מחשבים. כאילו, זה איך מה שבאתי, כן? בגלל קצת יותר בפורמלי. או כאילו שיש להם ליגה. ומה אתה בתואר ראשון?
עשיתי 3 שנים של כימיה ופיזיקה 2 של פיזיקה.
מכיר אותו שוט? שטיינגל? ביולוגיה כימיה? שם מצוטט הזה? רגע, עשית כאן בעברית?
כן, אבל סיימתי לפני 4 שנים.
אוקיי, אז ככה לא. הפסקה נחמדה.